So the last poster is achieving 54 plus gigahertz using optimized socket architecture with traditional probe technology for low cost of test. Our presenter today is Peter Cockburn from Cohu.
Hi, my name is Peter Cockburn of Cohu Incorporated, and this presentation will describe a technique to combine traditional spring probe technology with a dielectric optimized socket architecture to reach greater than 54 GHz frequencies and deliver high yield with low cost of test. At Cohu, we call this the C-Racer concept. After summarizing the key features and benefits of the C-Racer concept and the intended frequency coverage, I will use a specific example to show how it is applied and verified. The C-Racer concept uses traditional spring probe technology with a dielectric optimized socket architecture. This process can be applied across a range of pitches, allowing wafer probe solutions to be developed at 150 micron pitch, as well as a variety of package test solutions at pitches up to 650 microns. The technique uses a range of qualified materials for the socket housing to address requirements for low cost, good mechanical performance, and high-frequency test. Various probe tips and test heights are available to meet different package contacting needs. The reason for developing C-Racer is that as the industry moves towards wider 5G deployment, the focus is shifting from sub-6 GHz FR1 to 5G millimeter wave FR2 at up to 52.6 GHz. This will require new contactor technology that meets both the performance and lower cost requirements for high-volume deployment. C-Racer solutions have been developed to address this FR2 frequency range, and they complement higher price performance options using coaxial or coplanar lead frame technologies. The C-Racer process starts with a probe technology chosen to match the required pitch and tip profile for the package or WLCSP to be tested. These are combined with a sandwich of various materials that form the contactor housing, which may include a body and spacer, probe retainer plate, and either a fixed or floating alignment plate. Each of these layers in the contactor housing will have dielectric properties that affect the impedance and frequency performance of the overall system. Adjusting the relative thickness of these layers and selecting different materials allows a tuning process to be performed to better match the required overall impedance, usually 50 ohms. At each stage of the optimization, RF simulation is used to verify the expected performance in the required probe configuration, which is usually ground signal ground or sometimes ground signal signal ground for SerDes ports. After the final simulation indicates the required performance is being achieved, a sample contactor or test fixture is built using the selected materials. This is tested using a 2-port high-bandwidth VNA to verify the actual insertion loss and return loss performance are achieved versus the simulation. The spring probes in the assembled contactor are measured using test probes that match the required pitch and can compress the C-Racer probes to the required test height. This may require a special test jig to hold all the required components rigidly in place and allow for micro-adjustments in position. In one example application that was developed at 150 micron pitch, the RF bandwidth provided by a spring probe when used in a standard cross-section was around 20 GHz when measured. The same spring probe was used in a C-Racer optimized cross-section with different layers of material that better matched the overall dielectric requirements. After measurement, this was confirmed to meet the simulated target performance of 54 GHz. To summarize and conclude, the C-Racer optimization technique has been used to extend RF bandwidth from around 20 GHz to more than 50 GHz. The technique is being applied to a range of spring probes that can be used in applications at pitches from 150 micron to 650 micron, and these are being deployed at customers to address emerging 5G test challenges. As mentioned before, the C-racer technique can be used to complement higher price performance options using coaxial or coplanar lead frame technologies, and it offers a more cost-effective solution for high-volume production by maximizing the effectiveness of standard spring probe technologies.
Peter, I had one. Peter,
Okay.
when you say standard probe technologies, right? What kind of material, I guess, tip material do you comprehend in that? Can we put in anything that is available in the market, or is it a certain range of materials and hardnesses and so on and so forth?
I mean, the probe tips are typically going to be based on what you're testing. So, I mean, we have a variety of standard duct plunger and probe tip options, some of which are proprietary. I guess depending on whether you're testing an LGA, with a flat pad or a sort of BGA solder bump, we can sort of choose those accordingly. We're sort of starting off with materials like beryllium copper or palladium alloy, and then we have various coating options as well. But that's not really affecting the RF performance. It's more related to the contactor housing and the layers of material in that and the relative thicknesses.
Thank you.
I want to once again thank our sponsors who have made this event possible, our premier sponsor, Cohu, our emeritus sponsor, JonsTech, our honored sponsors, ISC, iWind, and TSC, our distinguished sponsors, Backer Hotwatt, Innovative Circuits Engineering, JMT, Nidec SVTCL, R&D Altanova, and UI Green, and our exhibitor sponsors, ELES, MJC, Phoenix Test Arrays, and Smiths Interconnect. So when you have a chance, please thank these companies for sponsoring, which has made this event possible and has made it available free of charge. And once again, I would like to thank Cohu, our premier sponsor, the market leader in test interface solutions for the most challenging applications, and ISC, the global #1 total test solution provider. So we thank them both for their leadership. And once again, I thank everybody for attending, and we look forward to seeing you again tomorrow at 7 a.m. Pacific. Thank you.